Okay, so welcome back. So now I can answer your questions about our discussions in the last part. Then I will give you more examples that you can work on. Okay, if something is not clear, if you want me to go over the material once again, I can do it. So everybody's happy. Everybody got entire thing perfectly done. I'm not seeing any hands raised. Okay. All right then. So previously I tried to write an example, but I kind of messed up with the dimensions. So here's the problem. So again, this is a minimization problem. There is no inequality constraint. There is no non-negativity constraint. As you see from this, you see x could be positive or negative. And there is this vector theta, and there is this matrix phi. Okay, so what's happening here? So there is this phi x. So I multiply the matrix phi with x. X is my choice vector. Okay, so x1, x2, dot, 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 xp are my choice variables. So phi x is itself, of course, a vector. Then I subtract this vector from my theta vector. Then I take the transpose of this, right? So so theta minus phi x is k by 1. So if I take the transpose, it is 1 by k. Then I multiply it by itself. So this becomes the dot product or inner product. Okay. So this is generally called a quadratic form. So from a mathematical point of view, it is called a quadratic form because I'm multiplying it by itself, right? And this is a minimization problem, so you can solve it. Okay. There's actually a nice there are nice tricks for taking derivatives of vectors and matrices, but I will not go into this detail, and I will not go into solve this problem, but this is a very familiar problem to you. Okay, this is ordinary least squares if you look at it carefully. Okay, this is an econometric problem. How? Well, this is your y variable. Okay, just a sec. This is your y variable. This is your x variables. So you have p different explanatory variables. K is your sample size. And this is your beta, right? So y minus x beta is your error term. Okay? So you are minimizing this. So in other words, you have from I equals from I equal 1 to k, okay, epsilon I squared. Okay, this is least squares. Then, of course, you can define other estimators by using the weighting matrices. Okay, k by k weighting matrices. You can develop many different estimators in this way. Okay, so this was just an example, but in principle, if you want to do very quickly with the vector notation, you can check Green. There's this econometrics textbook, William Green. In this textbook's appendix, I guess, he teaches how to take derivatives of the vectors and matrices. Okay. So let me give you another problem. Okay. Let me give you another problem. So suppose that there is this person who benefits from consumption of a particular good, plus also benefits from the number of kids he or she has. Okay, so C is consumption, and N is, let's say, fertility. Okay. Now, consumption will be, of course, non-negative. Okay. And fertility will be a bit different. There could be 0, no kids, and then there is this maximum. Okay. So where does this maximum coming from? It's coming from biology. Okay, it's coming from your lifetime resources. So in your lifetime as a woman, let's say, there is this particular age interval that you can have kids. Okay, so this means since each pregnancy also takes time, there is a maximum. Okay, so there's a minimum. The minimum is 0, obviously, and there's a maximum fertility, which is a biological or time-related constraint. Okay, and then let's imagine a budget constraint. So let's say you are paying PC for the consumption good, and then you are also feeding your kids. Okay, and you have a total income of W. So in this problem, you have a parameter beta, which is greater than 0. There's a price, which is an exogenous variable, which is greater than 0. Psi governs the cost of fertility, and income is your other explanatory variable, exogenous variable, and which is also fixed. Okay, and then there's eta, of course. Okay, so the Lagrange of this problem. So again, your choice variables, and there is one budget constraint, so you can, of course, write it in this way. So you have ln C beta n plus lambda W minus PC minus psi n. Okay, so let's check the first of the conditions. So again, let me write the Lagrange once again. So it is ln C plus beta n lambda W minus PC psi n, right? So for C, you have 1 over C minus lambda P less than or equal to 0, C times this equal to 0, and C greater than or equal to 0. Now for N, it is slightly different. So you have beta, okay, beta. Then you have minus lambda psi, okay. Now be careful. You have to be careful here because originally in our original formulation, our non-negativity constraint looks like this, right? So there was no upper bound. Now there's an upper bound, and I want to consider two possibilities now. There's 0 and there's eta, right? Right? So there could be a maximum there, okay? Or there could be a maximum there, right? So how should I write this condition then? Well, it could be less than 0, equal to 0, greater than or equal to 0, right? And obviously n beta minus lambda psi will again be greater than 0, but here n is equal to 0. Here n is between open interval, careful, 0 and eta, and here n is equal to eta. You see? So if there is an upper bound, then you must be careful with this boundary solution as well. Okay? Then you have the constraint. So you have W PC psi n greater than or equal to 0. And then you have lambda times W minus PC minus psi n equal to 0. And then you have lambda greater than or equal to 0. Okay. Now, realize that C is always positive, right? We discussed this last week. If C goes to 0, it violates the first order condition with respect to C. Okay? So then there are three possibilities for N. N could be 0. N is between 0 and eta. And N equals eta. Okay? So we're going to check three possibilities. All right? So let's do that. First of all, let me use this space for some derivations. Okay, so I know that C is greater than 0 in any case. So I have 1 over C equals lambda P. So from this, I know lambda is equal to 1 over PC. Okay, so it is greater than 0. If lambda is greater than 0, I know that budget constraint holds with perfect equality. Okay, then there are now different cases. Okay, in case 1, I have beta less than or equal to lambda C, right? N is equal to 0. In the second case, beta exactly equals lambda C. Okay. And then in the third case, I have beta greater than equal to lambda C. All right. So again, lambda is equal to 1 over PC. W is equal to PC plus Cn. Now in the first case, N is equal to 0. If N is equal to 0, I have W equals PC, right? So from this, C is equal to W over P, the real wage, all right? If that's true, then lambda is equal to 1 over income, right? Because PC is just W. And again, this is greater than 0. Now, what was my constraint? My constraint told me that beta should be less than or equal to lambda W, right? Is that correct? Let me check. Sorry, lambda C. I'm sorry. So beta should be less than or equal to lambda C. Now, what is lambda? Lambda is 1 over W. So I have C here. So if, let me just write this in terms of wages. If wage is less than or equal to psi divided by beta, then N equals 0 does not violate my first order necessary conditions. Right? Nice. Case 2. N is between 0 and eta. Okay? Now in that case, the budget constraint is this. W equals PC plus psi n. Lambda equals 1 over PC. Okay? And since n is between 0 and eta, I also have beta equals lambda c. Okay? Now, as you see, this is 3 equations in 3 unknowns. How do you solve it? First, you got lambda. Lambda is equal to beta divided by c. Okay, knowing lambda, c is equal to 1 over p lambda. So c is equal to 1 over P times beta psi, okay? In other words, it is psi divided by P beta. Then N is equal to what? N is equal to W minus PC divided by Psi. So it is W income minus P times C. P times C is Psi beta, right? P times C is Psi divided by beta, and you have Psi here. You can just write it in this way. Beta W minus Psi divided by beta Psi. Now, obviously, this must be between 0 and eta, okay? This must be between 0 and eta. Now, in the third case, what do you have? You have N equals eta, okay? Now, if N is equal to eta, from the budget constraint, you know PC psi eta, right? So C is equal to W minus psi eta divided by P. Then, of course, your lambda is 1 over PC. It is still true. So it is W minus psi eta. Okay? Now, clearly, this must be also greater than or equal to 0, right? And also, since N is equal to eta, you have beta greater than or equal to lambda psi. So for each case, as you see, you're going to find conditions. Okay? For each case, you're going to find these conditions and you're going to summarize these conditions. In the first case, what do you learn? If wage is sufficiently low, if you are sufficiently poor, you are not having kids. Okay? Here, there will be further, let me use a different color. So in the third case, look what's happening. So you need W minus psi eta greater than or equal to 0, right? In fact, strictly greater than 0. Why? Because lambda is strictly greater than 0. Okay? Look at the denominator. So you have W strictly greater than psi eta. Okay? Then you find your characterization, I guess. This is your income, and there are two thresholds. Okay? Two thresholds. The first threshold is psi beta. The other threshold is psi eta. Okay? Now, of course, this characterization also requires psi beta to be less than psi eta. In other words, 1 over beta to be less than eta. Okay? Then you can tell me that if wage is less than W beta, it is 0. If wage is greater than psi eta, it is maximum. So here it is eta. So this variable is n. Okay. This is 0. This is eta. And then in between, it is increasing with income. You see, linearly. So you have that, right? So let me show what is happening here. So this affects that. This and this determine that, and this, the solution you see here, shows you that it is linearly increasing in income. So if you think about this, if you start thinking about this as a historical case, economies are poor. Okay, a person is poor, let's say, not an economy, but a person is poor. When he or she is poor, he doesn't have kids because there's not enough income. Then after some period, after some threshold, let's say he or she finds a good job, a better job, let's say, then he starts accumulating some assets, and then he or she have kids. When income is getting larger, the first kid, the second kid, the third kid, right? At least 3 children, as our president says. Then at some point, I'm so rich, but I'm already old. I'm more than 50, so I cannot have kids. Okay? Something like that. So I showed you this example basically because you have to be careful with the upper bounds as well, right? In some problem, there could be some upper bound. Okay, when there's an upper bound, you're going to remember what happens on the other side of the boundary. Okay, not just at 0, but also at eta. Okay, now do you have any questions about this? Okay, then check the second order conditions. Okay, now we already have the constraint, and the constraint is so this is your gx function, and since this is linear, it is concave, right? Linear, so it satisfies concavity. Our objective function is, our f of x is natural logarithm of c plus beta n, where beta is positive and c and n are non-negative. Okay? So how to check this? Now, if you look at the bordered Hessian, what do you have? Remember, first, there is 0 here. Then first order derivatives. 1 over c beta. 1 over c beta. Okay? Then the second order derivatives. So this will be fcc. This will be fcn. This will be fnc. This will be fnn. Right? So what do I have? 0, 1 over c beta. 0, 1 over c beta. I have the second derivative, so it is minus 1 divided by c squared, right? Then I have 0. Then I have 0. Then, since the first derivative is beta, the second derivative is 0. Okay? So how to check that this function is strictly quasi-concave, or just quasi-concave, of course? Well, the first one, first determinant I'm going to look at is just this, and it is directly 0. Sorry, directly negative, right? Because it is 0 times minus 1 over c squared minus 1 over c times 1 over c. So it is minus 1 over c squared, always negative. Now in the second one, I need that. All right? So how do you take the determinant? Well, I usually do the row expansion. You can do whatever preferred choice of yours. So 0, 1 over c beta, 1 over c beta, minus c to the minus 2, 0, 0, 0. My preferred way is to do row expansion. So I choose a row. I will choose the row with the maximum number of zeros, right? So here, this element, so this is, of course, the determinant of B itself. So first, I have beta. Then I have minus 1 plus I plus j to the I flat. So I is the row, j is the column. So the row is 3, the column is 1, right? So this is just 4. So this is equal to plus 1. Then I'm closing that row. So the rest is 1 over c beta minus 1 over c squared and 0. Okay? So I have beta times 0 times 1 over c minus 1 c to the minus 2 times beta. So I have beta 0 plus beta divided by c2, so it will be plus. So I have beta square c squared. And it is always, as you see, positive. So as you see, the first is always negative. The second is positive. So for quasi-concavity, I need that. B1 less than 0. This is always satisfied. B2 greater than or equal to 0. B3 less than or equal to 0. And that goes on. For strict quasi-concavity, I need, again, beta 1. This is always less than 0. But beta 2 strictly greater than 0. Beta 3 strictly less than 0. And that goes on. And as you see, I have strict quasi-concavity here. Okay? So my F is strictly quasi-concave. My G is concave. And then I have the solution. Okay? In general, I recommend directly checking at quasi-concavity. Okay? Not concavity, but quasi-concavity. Now, of course, there are other conditions, right? Remember our other conditions. Remember theorem 2.4.
Sorry, can I ask a question?
Yes, so go on.
We use direct theorem 2.4, right? You suggest that?
Yes. In general, I mean, it depends on the, of course, function, but here you are not exactly sure whether your function is concave, right? Because there is this linear part, beta n. So some of the time, most of the time, you cannot directly see whether a function is concave or quasi-concave. All right. So I would recommend, if it is, I mean, in this problem, it is obvious, right? Remember the OLS problem. In OLS problem, it is pretty obvious that this is strictly convex, okay? Because this is a quadratic form. So if you write this, so it is square there, right? So sometimes it is easy to see. Some other times it's not easy to see, so, right? So look at this. So yes, this part is concave, but this part is linear, so maybe it confuses you, something like that. Okay, and of course, you can also check Hessian, right? Your Hessian matrix is this: 1 over minus 1 over c squared, 0, 0, 0. Okay, so what do you learn from this matrix? You're going to check whether it is negative definite or not, right? But it becomes inconclusive. Why? Because, so let me just make sure. So the first, okay, it is negative, 1 over c squared. The second is 0. So it is concave, but not strictly. So you cannot say it is strictly concave. And actually, you can see that it is not strictly concave from here, obviously. So it depends on your choice. But if you are using theorem 2.4, you're going to check one of the other conditions. Okay? Now, I was just talking about that. So there are 4 other conditions, remember. Right?
Yes.
Now, we actually just did the last one. F is concave. Right? The last one, I guess, saying that F should be concave.
Yes.
Okay, so we just do that. Sometimes it may be, I mean, I think the third or the second one, I thought, I mean, go ahead. Go ahead, we are listening. Is there a question? Okay, let me continue then. So I'm not quite sure which one was that, but one of the conditions is typically satisfied in economic problems, either second or the third one. I discussed that last point. So it is f prime x greater than 0 at the optimum. Okay. In here, for instance, what do you have? You have 1 over c squared, right? If c is that variable that can violate g, remember that theorem. And for g, the first order derivative is always positive in optimum. Okay. Again, I mean, so this is a question of philosophy or methodology. If you constructed your problem with enough care, if you know what you are doing, then most possibly you either satisfy theorem 2.2 or theorem 2.4. If you are trying to maximize a convex function, okay, if you are trying to minimize a quasi-concave function, then you are in trouble. Your trouble is bigger, okay? Because your problem is not well structured. Or, of course, I mean, the problem is given to you. You are not designing your problem. The problem is given to you as if you're a student and there's a teacher there and he or she assigns problems. Then, of course, you're going to check whether it is concave or convex or quasi-concave or quasi-convex. Okay?
Thank you.
All right. So I have about 3 minutes. Let me define a new problem. So imagine that there are parents, and these parents care about the human capital of their kids. Okay? H is human capital. So C is, again, consumption. And you can actually imagine they care about the human capital of their kids. So C is parents' consumption. H is human capital of the child. Imagine that there's one child. There could be more than one child, but just imagine that there's one child. Okay. Now there is this, of course, human capital technology. Okay. So if you if you let's say if you send your kid to the school and spend $E, okay, then your kid has this level of skill at the end. Okay, so here eta is positive and gamma is between 0 and 1. So there is diminishing returns. Okay, you can increase your education spending, but that cannot, so that increases human capital, but in a slower and slower pace. Okay, so there are diminishing returns. Now, why there is 1 here? I mean, it doesn't have to be 1 actually. So let me change that. Let's say it is beta. Okay. Now, if E is equal to 0, if you do not spend anything for your child's education, then H0, obviously, because this is a function HE, right? H0 is eta, beta, gamma. Okay? So you may imagine this. There is this education spending and there is this human capital. So if education spending is 0, human capital is equal to some level, all right? And then, sorry. If E is 0, wait, I'm confused. I couldn't draw it. I'm sorry. So okay, let me check this over the break. So we have less than a minute. Let's meet at 2:50. Is that good? 2:50. Okay.
Okay.
All right.
Okay.
Okay. Bye bye.